This lecture is about the paradigmatic relation discovery. In this lecture, we are going to talk about how to discover a particular kind of word associations called paradigmatic relations. By definition, two words are paradigmatically related if they share similar contexts. Namely, they occur in similar positions in text. So naturally, our idea for discovering such a relation is to look at the context of each word and then try to compute the similarity of those contexts. So here's an example of context of a word, cat. Here I have taken the word cat out of the context. And you can see we are seeing some remaining words in the sentences that contain cat. Now we can do the same thing for another word like a dog. So in general, we would like to capture such a context and then try to assess the similarity of the context of a cat and the context of a word like a dog. So now the question is, how can we formally represent the context and then define the similarity function? So first, we note that the context actually contains a lot of words. So they can be regarded as a pseudo-document, an imagined document. But there are also different ways of looking at the context. For example, we can look at the word that occurs before the word cat. We can call this context left one context. Right, so in this case, you will see words like my, his, or big, a, the, etc. These are the words that can occur to the left of the word cat. So we say my cat, his cat, big cat, a cat, etc. Similarly, we can also collect the words that occur right after the word cat. We can call this context right one. And here we see words like eats, ate, is, has, etc. Or more generally, we can look at all the words in the window of text around the word cat. Here, let's say we can take a window of 8 words around the word cat. We call this context window 8. Now, of course, you can see all the words from left or from right. And so we have a bag of words in general to represent the context. Now, such a word-based representation would actually give us an interesting way to define the perspective of measuring the similarity. Because if you look at just the similarity of left one, then we'll see words that share just the words in the left context. And we kind of ignored the other words that are also in the general context. So that gives us one perspective to measure the similarity. And similarly, if we only use the right one context, we'll capture the similarity from another perspective. Using both left one and right one, of course, would allow us to capture the similarity with even more strict criteria. So in general, context may contain adjacent words like eats and my that you see here, or non-adjacent words like Saturday, Tuesday, or some other words in the context. And this flexibility also allows us to measure the similarity in somewhat different ways. Sometimes this is useful as we might want to capture similarity based on general content that would give us loosely related paradigmatic relations. Whereas if you use only the words immediately to the left and to the right of the word, then you likely will capture words that are very much related by their syntactic categories and semantics. So the general idea of discovering paradigmatic relations is to compute the similarity of context of two words. So here, for example, we can measure the similarity of cat and dog based on the similarity of their contexts. In general, we can combine all kinds of views of the context, and so the similarity function is in general a combination of similarities on different contexts. And of course, we can also assign weights to these different similarities to allow us to focus more on a particular kind of context. And this would be naturally application specific. But again, here the main idea for discovering paradigmatically related words is to compute the similarity of their context. So next, let's see how we exactly compute these similarity functions. Now, to answer this question, it's useful to think of bag of words representation as vectors in the vector space model. Now, those of you who have been familiar with information retrieval or text retrieval techniques would realize that the vector space model has been used frequently for modeling documents and queries for search. But here we also find it convenient to model the context of a word for paradigmatic relation discovery. So the idea of this approach is to view each word in our vocabulary as defining one dimension in a high-dimensional space. So we have n words in total in the vocabulary, then we have n dimensions, as illustrated here. And on the bottom, you can see a frequency vector representing a context. And here we see when eats occurred 5 times in this context, 8 occurred 3 times, etc. So this vector can then be placed in this vector space model. So in general, we can represent a pseudo document or context of a cat as one vector, D1. And another word, dog, might give us a different context, so D2. And then we can measure the similarity of these two vectors. So by viewing context in the vector space model, we convert the problem of paradigmatic relation discovery into the problem of computing the vectors and their similarity. So the two questions that we have to address are first, how to compute each vector, and that is how to compute xi or yi. And the other question is, how do you compute the similarity? Now, in general, there are many approaches that can be used to solve the problem, and most of them are developed for information retrieval. And they have been shown to work well for matching a query vector and a document vector. But we can adapt many of the ideas to compute the similarity of context documents for our purpose here. So let's first look at the one possible approach, where we try to measure the similarity of context based on the expected overlap of words, and we call this EOWC. So the idea here is to represent a context by a word vector where each word has a weight that's equal to the probability that a randomly picked word from this document vector is this word. So in other words, xi is defined as the normalized count of word wi in the context. And this can be interpreted as a probability that you would actually pick this word from D1 if you randomly pick the word. Now, of course, these xi's would sum to 1 because they are normalized frequencies. And this means the vector is actually a probability distribution over words. So the vector D2 can be also computed in the same way. And this would give us then two probability distributions representing two contexts. So that addressed the problem how to compute the vectors. Now next, let's see how we can define similarity in this approach. Well, here we simply define the similarity as a dot product of two vectors. And this is defined as the sum of the products of all the corresponding elements of the two vectors. Now, it's interesting to see that this similarity function actually has a nice interpretation. And that is this dot product, in fact, gives us the probability that to randomly pick the words from the two contexts are identical. That means if we try to pick a word from one context and try to pick another word from another context, we can then ask the question, are they identical? If the two contexts are very similar, then we should expect that we frequently will see the two words picked from the two contexts are identical. If they are very different, then the chance of seeing identical words being picked from the two contexts would be small. So this intuitively makes sense, right, for measuring similarity of contexts. Now you might want to also take a look at the exact formulas and to see why this can be interpreted as the probability that two randomly picked words are identical. Right? So if you just stare at the formula to check what's inside this sum, then you will see basically in each case it gives us the probability that we'll see an overlap on a particular word, wi, and where xi gives us the probability that we'll pick this particular word from d1, and y sub I gives us the probability of picking this word from d2. And when we pick the same word from the two contexts, then we have an identical pick. Right? So that's one possible approach, EOWC, expected overlap of words in context. Now, as always, we would like to assess whether this approach would work well. Now, of course, ultimately we have to test the approach with real data and see if it gives us really semantically related words. Right? It really gives us paradigmatic relations. But analytically, we can also analyze this formula a little bit. So first, as I said, it does make sense, right? Because this formula will give a higher score if there is more overlap between the two contexts. So that's exactly what we want. But if you analyze the formula more carefully, then you also see there might be some potential problems. And specifically, there are two potential problems. First, it might favor matching one frequent term very well over matching more distinct terms. And that is because in the dot product, if one element has a high value, and this element is shared by both contexts, and it contributes a lot to the overall sum. And it might indeed make the score higher than in another case where the two vectors actually have a lot of overlap in different terms, but each term has a relatively low frequency. So this may not be desirable. Of course, this might be desirable in some other cases, but in our case, we should intuitively prefer a case where we match more different terms in the context, so that we have more confidence in saying that the two words indeed occur in similar context. If you only rely on one term, and that's a little bit questionable, it may not be robust. Now the second problem is that it treats every word equally, right? So if you match on a word like the, and match, it will be the same as matching on a word like eats. But intuitively, we know matching the isn't really surprising because the occurs everywhere. So matching the is not as such a strong evidence as matching a word like eats, which doesn't occur frequently. So this is another problem of this approach. In the next lecture, we're going to talk about how to address these problems.